busy here, kind of.
Very dry place, right?
Yeah, busy is good, and sometimes can be hectic, but overall, it's nice. Yeah.
So you teach science in high school?
Yeah, I teach yeah, science and math, and also art
Also
classes
art.
like
Okay.
He's a phenomenal
drawing.
artist, right? So he has
Yeah,
to.
you get periodic boundary conditions. You go extreme science, you become artist.
That's very
It's like they go hand by hand in a
Yeah.
way. Yeah. So
when Sunny was my student, my papers looked so much better. Uh, now the quality has really fallen.
Uh-oh. I think Essenio is sitting there somewhere.
All right, let's get going. So today it is a real pleasure to host my dear colleague, Professor Xuedong Hu. Xuedong arrived in Buffalo in the early part of the century, and I'll give you a little bit more detail, but he'll talk about physical implementation of quantum bits, spin qubits in silicon. He claims he arrived in 2002, which probably is reasonable. Xuedong did his PhD from the University of Michigan.
Claim? Actually, I didn't arrive in 2002. Yeah.
You arrived in 2003, January?
Right, exactly.
I somehow had some doubt about that number. So at any rate, Xuedong arrived in January 2003 and is currently a professor of physics and also our very able director of graduate studies. He obtained his undergraduate degree from Beijing, 1989, I believe, and his PhD from the University of Michigan. He worked with Frank Honori when he was there. And then he trained as a condensed matter theorist, obviously, and went to work for Shankar Das Sharma at the University of Maryland as a postdoc. And he has been laser focused on quantum computing related problems pretty much for the last 18 years now. So it's a real pleasure to welcome Xuedong. And with that, I'm not going to take up any more of your time. It's all yours, and let's mute ourselves. And if you have questions, as usual, you can unmute yourself and ask it as we go along. Thank you.
Thank you, Surjit. Yeah, actually, I was supposed to get here in the fall of 2002, but I asked Bruce to give me a leave of absence to visit Japan.
Mm-hmm.
And actually, that was really helpful because I got to talk to some really good experimentalists. And several of my earliest, independent research projects grew out of that. So that was really, really helpful.
So Franco was there already. You spent time...
No.
Oh,
wait. Yeah, right. Franco went there earlier in 2002, I think, in the spring of 2002. Yeah, so I went there for a conference, and then I stayed with Franco for a couple months there. Yeah.
Yeah, I remember you had more fun than I did when I began.
All right. Okay, so I'm, as Surjit was saying, I have been really sort of focused on studying physical implementations of qubits, particularly in solid state structures. And in recent years, really focus on spin qubits in silicon. In a sense, we're steered by the funding we got, right? So, and that really takes up a lot of time. So I would really want to get into some other projects that along the way, it's always a question of time. But anyway, so today I'm going to just give you my perspective on, studying qubits, particularly in solids and particularly in semiconductors. But I'm going to also give sort of an overview where we were and where we are, and give you an example of what kind of things I have done or my group members have done here. That's probably going to be very brief because the history of qubits is quite interesting, and also comparing different type of qubits is also quite an interesting thing to do. Okay, So let me acknowledge my collaborators. Pei Hao and Xin Yu were my postdocs over the past 10 or so years. They have all moved on. Bilal and Zhang Chuang are two of my current students. Although the results I will show probably will only come out of Bilal. And I have several other current students who are at different stages of finishing up their research projects. Okay, and we have been fortunate to have support from the Army Research Office for all these years. So let's start with just think about what is it that a quantum system can really help us. I guess we all learned early on when we studied quantum mechanics that in the quantum world you have particle-wave duality. That any particle you thought about, let's say electrons or protons, they also have wave properties. So you can imagine a Mach-Zehnder interferometer, which obviously was originally devised for photons for light, right? And for optical waves, where you can observe interference effect when you change the relative length of the two optical paths. But it turns out you can do the same kind of experiment with electrons or protons. And I think the largest molecules people have been able to demonstrate this was with carbon-60. So that's a pretty large molecule, right? The Broglie wavelength is pretty short, but still interference phenomena were observed for them. Okay, so that's one of the key features for a quantum system. When you come down to bits, so I think one of the most important thing for us is for a quantum computer or for quantum bits is this exponentially large Hilbert space and the fact that you can actually build quantum states that are superpositions of different basis states, right? So, just look at this example of 3 two-level systems, so 3 qubits, so 3 quantum bits. Each can take a state of 0 or 1 or any superposition. So for the 3 qubits, the basis sets is 2 to the 3, right? It's 8 bases. And the good thing in quantum mechanics is if you make a manipulation on any one of those qubits, you're actually operating on all 8 states. Okay, if you actually prepare the system into a superposition of all those 8 basis states. So this is in strong contrast with classical bits, right? The classical, if you think about a sort of a corresponding Hilbert space, it is also exponentially large. But at any particular time, a classical system can sit only in one of these guys, in one of these states, okay? So after some time, after your manipulation, a classical computer will only go through one possible trajectory, starting from initial state, go through all the manipulation and end up with a definitive final state, right? So that's just one path. On the other hand, a quantum mechanical system, here, for example, for a 3 qubit system, when you do manipulations, if you initially put the system into superposition of the whole Hilbert space, it's possible. And then you do manipulation, then you're exploring all the 2 to the n path. Okay. And you can have interference, it's waves, right? So you can have interference, you can, have all sorts of manipulations you can apply to. So that means you're really exploring the whole Hilbert space at once. Okay, so this is the so-called quantum parallelism, which really gave a quantum computer a huge power in terms of, how it can process information. Now, obviously, in quantum, when you do measurement, you're going to collapse those states. You're going to only measure one of them, right? So what you need, all the quantum algorithms that exist, basically design the algorithm such that you have an interference at the end, where only a few states probability gets enhanced. So if you repeat the algorithm a few times, you're bound to hit the right state. and then you can get what you want. Okay, so that sort of underlies these famous algorithms like Shor's algorithm for factoring and Grover's algorithm for short sorting. Okay, and also, you know, these days people also talk about for smaller scale quantum computer, you can do quantum simulations. But you know, this quantum parallelism together with interference and measurements can really make a quantum computer much more powerful than classical computer for certain tasks. Okay, not for everything. Like for our word processing on your computer, or just to add 1 with 1, to multiply two numbers, those things, classical algorithms are as powerful as quantum ones. The quantum algorithms generally is always, you know, what makes it powerful is it can actually survey the whole system. It looks for global properties. Okay, that's when a quantum algorithm could have a huge advantage, right? Because it goes through the whole space, whole Hilbert space. All right, so that's sort of a very simple introduction to quantum computing. And so the quantum computing really sort of took to flight back in the middle of 1990s after Shor's algorithm, and after Peter Shor and a couple other people developed quantum error correction techniques, which basically says that in principle, you could potentially make a quantum computer. So since then people start to think, right? You know, as Rolf Landauer said back in the 90s, information is physical. So if you want to make a bit, you have to identify a physical system that actually give you a bit, a quantum bit. Okay, so one of the earliest proposal is this system based on liquid state NMR. Okay, so basically this is it's not a true quantum computer in the sense of, you know, several single qubits, you manipulate them. Here you have, you know, billions, trillions of molecules. They're all the same. And each molecule has a few different, for example, like this molecule has a few different ions you can, spins that you can identify, like 1, 2, 3, etc., based on their environment, right? You know, for example, this, I think is fluoride, is next to a carbon and another carbon here. This fluoride, on the other hand, is next to a carbon and next to a fluoride, etc. So they have all slightly different environment, and then you can, through frequency, you can distinguish these different fluoride and nuclear spins. Okay, so, and liquid state, the molecules keep tumbling around, right? So that gave you the so-called motional narrowing, which make the quantum state quite coherent. Okay, so you can't really prepare these molecules initial states, but in a finite temperature, there's always, you know, the ground state is always has lower energy than the excited state. So you can sort of do ensemble average, and at the end, actually extract information when you try to manipulate these nuclear spins. So this is one of the earliest. I think people use this to demonstrate using Shor's algorithm to factor 15 back in 1999 or something like that. Okay, so it's a very good demonstrator. It's not a scalable system. You know, to make it scalable, basically you make a molecule of millions of spins and still can distinguish them. That's just impossible, right? I think the largest molecule, these are custom designed molecules. I think as far as I can remember, it goes up to like 12 qubits. Okay, and then you run into issues like frequency crowding and things like that. So you can't really go further. But it's a good system that can help you learn how to do coherent control and also analyze what factors give you decoherence. Okay, so I don't think now there's many people really studying this as a qubit, although there might still be a few groups studying it to demonstrate, you know, ways to do control or ways to characterize density matrix. So the first really sort of breakthrough qubit is the so-called trapped ion qubit. These systems have been designed for atomic clock. Okay, so groups like in the US NIST or in Saclay in France, those groups have studied this system for a long, long time, or you know, in Austria, Innsbruck, there are some really impressive groups, and you know, a couple Nobel Prize have been given, right, for manipulating the nuclear spin states of these ions and observe their frequency really, really precisely to make atomic clock. And so very naturally, you can use this to do quantum information processing with individual ions, but that's just a single qubit. So back in 1997, Chirac and Zoller proposed that you can make an array of these ions in a linear trap, and then use the phonon, the ground state phonon, to mediate interaction between any pair of ions. Okay, so you know, you have a linear array of ions confined together by the external trap, and they interact with each other through Coulomb interaction, right? So you got a linear array, a crystal, and the crystal would have a vibrational mode. The ground state, the ground vibrational mode is the central mass mode. The whole array of ions oscillate in the trap. That's the phonon mode that can be taken advantage of. Okay. Now these systems are at very low temperatures, so you can imagine that you can cool the whole system down to the ground state for the vibrational motion. Okay, but the question then is, and you know, manipulation of these trapped ions have been demonstrated with very high fidelity. They are very slow because these are nuclear spin qubits, so nuclear spin frequency is very low, right? So often these are RF radio frequency processes, megahertz or something like that. But still, they can be controlled very well and measured with very high fidelity and everything. It's just that this particular step of you know, using the ground state vibration, that means you really need to cool it down. So the question then becomes, well, how do you scale this up, right? How do you make larger computer using this? You know, people proposed, like Chris Moreau and Dave Van Line, they proposed that you can make multiple arrays and you can shuttle them around, and you know, so you have storage arrays, you have manipulation areas where you do your quantum gates. But you can see immediately that this is somewhat contradictory in the sense that when you shuttle them around, you're moving, right? You have an orbital motion. When, on the other hand, when you really try to manipulate them, you need to go down to the ground vibrational mode. So each time after you shuttle, you have to cool it down. And hopefully you cool it down fast enough within the coherence time of everything else, and then you can perform this scheme. So it's a pretty difficult task within that sort of scheme. Okay. So from early on, we have been thinking about how can we do a quantum computer in solid state. You know, myself as a condensed matter theorist, and you know, people before me who made the proposals, they are all condensed matter people. So with the computer sitting in front of you, all solid state, it's natural, it's pretty natural to ask, right, whether we can make a quantum computer that is solid state, that doesn't fly apart when your trap potential has some, you know, glitch. Okay. So one of the earliest for that is a superconducting qubit. It's a so-called Cooper pair box. So what it is, you have a small piece of superconducting grain, okay, small in the sense of like micron size, in one dimension, 100 nanometer in other dimensions. So the charging energy is sufficiently large, okay. And then you can, when you put it in contact with another piece of superconductor with a thin insulating layer in between, you get a so-called Josephson junction, right? Where Cooper pairs can tunnel through that junction coherently. Okay. And so now this small superconducting grain, it already has probably billions of Cooper pair. But by controlling the Josephson junction or Josephson tunneling, you can put one extra pair or not to put that extra pair on the island. Okay. And so that gave you a basis for a qubit. So 0 extra Cooper pair or 1 extra Cooper pair. Okay. And these two states are separated from other, like 2 extra Cooper pair or whatever, by charging energy. So here is a simple Hamiltonian. You have a charging energy. N is the number of Cooper pairs on the island. And X here represents a gate potential, which you can use to tune the potential of this ion relative to the rest of the superconducting circuit. And EJ cosine phi give you the Josephson coupling. And N and phi are a pair of canonical variables. So you can write phi as just change of N. Okay. And so, if you just have that, you have a periodic potential, right? So it looks like this. And the Josephson coupling would actually break this apart and make it into a lower band and higher band and even higher bands, etc. Okay. And so we'll use this part by tuning the gate potential we can use here as our qubit. Right? We can prepare the system over here where the ground state is 0 extra pair, and we can shift to this part where the eigenstate would be superposition of 0 and 1, and the splitting of those two states would be the Josephson coupling. Okay, so you have a pretty simple qubit here where you can manipulate the system. Okay. And so this was actually first demonstrated experimentally back in 1999 by the Johnson Tsai group in NEC. So they made a Cooper pair box and then they made measurements. I didn't have a data set there. The coherence time was extremely short. These are charge qubit, right? You're using charge degree of freedom. So it's very sensitive to external, like environmental charge fluctuations. So the coherence time in that experiment was like 1 nanosecond. Truth is, they didn't really characterize it. It's probably even shorter than nanosecond. The oscillation, its magnitude is very small and very irregular. Okay, but still, anyway, it's a demonstration of a coherent oscillation. Now, there's a reason why this superconducting circuit was the first among the solid state system where you can demonstrate quantum coherent control. Because back in the 80s and 90s, people like Tony Leggett have been pushing to experimentalists to study the transition from quantum mechanics to classical mechanics. And he was proposing that you could observe the so-called microscopic quantum coherence in the Josephson junction system, okay, in the superconducting circuit, like a squid or a circuit of Josephson junctions. Okay, so there had been a lot of study of how to control these systems, and that really laid the technological foundation for all these progress after that. So when this qubit idea comes out, then quickly experimentalists can actually go ahead and do something with it. So this particular proposal, Cooper box, it uses the charge degree of freedom. Sort of a more amazing thing of a qubit is this so-called flux qubit. So basically you have a loop, which is broken by 3 Josephson junctions, also by, no, I think this is the qubit. Those are the detecting circuit. So this is the qubit, which is a loop broken by 3 Josephson junctions. And you can actually design the magnetic flux through the system so that the qubit actually is given by the current flowing, supercurrent, flowing one way, clockwise or counterclockwise. And those are your qubit states. So current flowing one way or another give you the qubit states. Okay. And this was demonstrated also pretty early on. I think the first experiment was done also in 1999 or maybe 2000. And this experiment done in Delft was really very high quality experiment. Okay. But even high quality, the coherence, excuse me. The coherence time of these systems are still pretty short, sub-microsecond. Okay. At that time, all the experiment on Cooper pair boxes also like that. In 2004, Saclay group in France designed an experiment and a qubit they called quantronium, which can reach a coherence time of half microsecond. They got to publish in Science, and it got a lot of people excited, thinking that, whoa, this is a very coherent system, right? Compared to the 1 or 10 nanosecond of the first Cooper pair box, surely this is a vast improvement. But still, all the manipulation requires tens to 100 nanosecond. So if your coherence time is only 500 nanosecond, you're going nowhere for this system as a qubit. So the real breakthrough came in back in 2007 or so, where people proposed that, well, because the charge noise is a hugely influential decoherence factor, so you got to find a way to shield your qubits from the charge noise. This is not only true for Cooper pair box, but also true for flux qubit, because flux qubit, those 3 Josephson junctions, 2 of them can be large, but 1 of them has to be a small junction. A small junction means a large charge coupling, large charging energy. So it turns out to be also sensitive to charge noise, in addition to flux noise. Okay. And so back then there were a couple of papers. This paper came out of Yale group, designed a so-called transmon qubit, which basically is using a huge capacitor to shunt the Josephson junction Cooper pair box qubit. Okay. And when you put this huge capacitor in parallel with your junction, the external noise turns out to mostly goes onto that capacitor, and so that its effect on the qubit is strongly suppressed. Okay, and so that vastly improved the quality of the qubit. And this design underlies most of the qubits that are currently being studied in different companies. It's the transmon type of design. Actually, this is a work I participated. It was mostly carried out by JQU when he was, I think he was already back in China, or he was visiting Franco Nori in Japan. And he also recognized that, for a flux qubit, you got to have one small junction, and that junction introduce charge noise into your system. So he also came up with the idea of doing a capacitively shunted flux qubit. Okay, so this system also can strongly suppress the sensitivity to charge noise by doing that capacitive shunting. And so right now there are still experimentalists trying to explore this system as well, or to actually use both of these designs on the same chip to try to improve the qubit fidelity. Okay, so this idea of sort of basically engineering away the decoherence or design shielding to shield your qubit away from the most influential environmental noise really improved the qubit greatly. So since then, this also, back in the middle of 2000s, the Yale group also demonstrated you can couple these superconducting qubits strongly with a resonator. So these are so-called strip-line resonators. And so that couples the superconducting qubit with microwave photons, okay? And they easily beat the strong coupling limit, which, the atomic physicists have been struggling for decades to try to reach that limit where the coupling strength is much stronger than the decoherence time. For this system, you beat that limit easily, okay? So this is sort of a lead to the growth of the so-called cavity QED or circuit QED systems where you can study QED problems. But anyway, so nowadays the qubits are mostly based on the transform design, as I mentioned. This is just a sort of schematics of Google's Sycamore chip, which underlies their experiment for the so-called quantum supremacy, where they demonstrated for some random number generator, they can beat a current supercomputer by quite a bit, okay, to show that a quantum computer actually is good. This one has, I remember, 53 or 52 qubits in it, okay. But more importantly, if you look at this figure, which came out of a review from Will Oliver's group, you can see the growth of coherence time from the early days, where the unit 1 here is microseconds. So the early days is like, 1 to 10 nanoseconds or a few nanoseconds. And the coherence time has been growing really almost exponentially, right? But, this is a big step. That's when the contronium or the sweet spot idea came out, okay? And then when you have the transmon was designed, and then you keep growing since then. Okay, so now a typical coherence time can reach at least hundreds of microseconds, and sometimes you can go higher. This higher qubit, I don't know how well you can really use it to make scalable qubits. Often, these experiments are customly designed, so a single qubit may have great coherence, but it's hard to put 2 of them together even. So that's different from this Sycamore type of system based on transmon, right? Where even when you put all of them together, your coherence time is still, for example, longer than 10 microseconds or something like that, okay? But anyway, you can see this really impressive growth of coherence time or the control of these superconducting qubits over the past 2 decades. And that leads to the fact that right now, superconducting qubit really is the dominant qubit that has been studied in different companies like Google, like IBM, Rigetti, etc. Okay. All right. So, one of the feature of these superconducting qubit is they would have these large capacitors attached to them, right? That's used to shield the noise. And with that large capacitor, if you look at the scale over here, this is 10 micron, and the horizontal size is the qubit, the capacitor. So that's like 100 micron, okay? So typically this qubit has a size of 100 to 1,000 microns, so sub-millimeter size, okay? And so you can certainly always ask, okay, with such a large qubit, can we really make a scalable system or not? I would say nobody can really claim they know. I think the people in the companies probably are more optimistic. At least they would act more optimistic. But it is a concern, right? It is a question mark, I would say. Okay, so I don't know whether they are truly scalable, and I don't think anyone can really say convincingly that they are. Okay, so it's a system that will certainly keep being explored and studied. And if I remember correctly, both Google and IBM claim they will reach several hundred qubits quickly within a year. Okay, so we'll see how things go. All right, so the system I have been studying, or a parallel solid state system that some people have been studying, is the spin qubit. So you take advantage of the electron spin, which is a spin half. So it's a natural 2-level system. You take advantage of that as a qubit, and in a solid state or in a semiconductor, you can confine these electrons to remove their orbital degree of freedom so that they become a purely spin qubit. And then you can try to manipulate them, right? Traditionally, you can think about using ESR to flip spins. And it turns out in the last Stephen Sensel proposal, one of the key idea they came up with is you can actually couple two spins very strongly, easily and strongly, okay? So if you go calculate the exchange coupling in, let's say, a gallium arsenide double dot, the exchange coupling can easily reach hundreds of micro electron volt or even milli electron volt, okay? And so that, you know, if you think about the interaction strength as the inverse of the gate time, then you can easily have a picosecond gate or 100 picosecond gate. Now, the control technology cannot reach that frequency. Right now, microwave control can reach a few gigahertz, right? So that's, you know, a couple nanosecond or nanosecond control, that's about it. If you want to control the pulses better, right? Because if you want a pulse that is 100 picosecond, then you have to control it at least to down to 1 picosecond so that the pulse can rise and fall with control. And that technology simply doesn't exist. Okay, so actually experimentalists don't go to large coupling, large exchange. Okay, so the spin qubit actually has this advantage that 2-qubit gate is actually easy to do, or at least it's a fast 2-qubit gate can be done in principle relatively easily. Okay, turns out the bottleneck here is a single qubit gate, because ESR, you know, which is magnetic dipole coupling, you use AC magnetic field to oscillate the rotate the spin. That's a weak interaction, so the gate time is easily microsecond. Okay, so it's turns out people have struggled quite a bit to try to improve that gate instead of the exchange gate. Okay, so this proposal came out back in it was actually devised, wrote out back in the beginning of '97, although it only eventually got published in '98. Okay, but this was a sort of a pretty interesting idea that get a lot of experimentalists excited. And so that led to other proposals as well. For example, Bruce Kane's proposal of using phosphorus in silicon to host qubit. The phosphorus 31 has a nuclear spin of spin 1/2, and they have 1 electron attached to them at low temperature, right, confined to them. These are shallow donors. So you can imagine if you use nuclear spin as a qubit, it will be greatly coherent. And you can use these electrons to mediate interactions between the nuclear spins. And that's the so-called Kane proposal. And later people realized that, well, the whole system's coherence is actually limited by these mediating electrons. So you might as well using the electron spin as a qubit, which is already very coherent. Okay, so right now, generally we are using the electron spins, not the nuclear spins, okay, for this sort of system. All right. But one sort of big holdback on spin qubits is, unlike the trapped ion qubit and the superconducting qubit, where experimentalists have laid the technological foundation for decades, or at least 10 years. Here with these systems, back in the late 1990s, there was no single electron lateral quantum dot, and there's no single spin measurement, right? A single spin is a Bohr magneton. It's such a small signal. Back then, the best magnetic measurement is using a squid, but you know, you can use a squid to measure a single spin signal for sure, but it needs a lot of time to collect the signal, okay, to make it large enough, to make the signal noise ratio large enough. So there's basically no practical way to measure a single spin. But people can measure single charge already. The development of single electron transistor technology already started back in the early 90s. So by this time, measuring single charge is easy. It's just that spin is just difficult, okay? And at that time, all the leading experimental groups work with gallium arsenide quantum dot because of the relationship to quantum Hall effect, right? You know, to study quantum Hall effect, especially for fractional quantum Hall effect, you need very high mobility, okay? And so, you know, people have developed the technology to make high mobilities gallium arsenide quantum wells, they are always much higher than silicon to start with. And the technology was keep being improved so that you can reach, let's say, 30 million mobility, right? Back in maybe already 10 years or 15 years ago. Okay, so naturally you think, okay, to make a high quality qubit, you would want a high mobility sample to start with. And gallium arsenide would be the one, right? And gallium arsenide has a very light electron mass. So you'd only need to make a large quantum dot already, you would have a confined system. Okay, so leading experimental groups all work with gallium arsenide back then. Okay, so that was the status. So to really have breakthrough for spin qubits, we need to realize a single electron dot and to be able to measure it. Okay. And so the single electron dot was first realized, or lateral quantum dot, which can be gate defined and can be characterized, can be scaled. These are developed by the by the NRC group in Canada. Okay, by the group from Andrew Sakrashta. So they developed, but by putting in gate designs that that deplete the quantum dot, but does not pinch off the tunnel barrier to the reservoir, they were able to actually design quantum dot and reach a single electron occupation for that quantum dot. Okay, so this happened back in 2000, and then personally, I think another really important breakthrough was this work on using spin blockade to measure. Now, this original paper is measuring current, so it's a rectification of current, but the principle behind it turns out to be the principle to measure a single spin, to couple spin with charge. Okay, so the basic idea here is if you have a 2-electron quantum dot, okay, you put 1 electron in each, the singlet and triplet state energy, the ground singlet and triplet energy state would be split a little bit, but very small, because the 2 electrons are, occupying 2 different dots, right? So the exchange splitting is only related to the tunnel coupling, and it's a very small quantity, okay? But if you put both electrons in a single quantum dot, now the singlet and triplet state, the spin, parallel spin state relative to the singlet, where you have an antisymmetric combination of spin up and down, that energy splitting becomes very large, because for singlet, you can put both electrons in the ground state, ground orbital state, okay? And in a small quantum dot, that splitting between the ground orbital state and the first excited orbital state would be several milli-electron volt, would be pretty large. And for a triplet, you cannot put both electrons in the ground orbital state, so you have to take one of them into that excited orbital state. Okay, so naturally you have a pretty large energy splitting between singlet and triplet if you have 2 electrons in a single dot. Okay, so this relationship between the charge distribution and the spin configuration, right? If you are in 1 electron in each dot, your singlet and triplet energy splitting is small. When you put both of them in 1 dot, the singlet triplet splitting is large. So taking advantage of this asymmetry, then we can actually correlate whether 2 electrons are in singlet or in triplet by looking at the orbital dynamics. So in this experiment, they measured the current and found out that in one biased direction, you have a region where current is strongly suppressed because of this so-called spin blockade. Okay, and this has become the sort of the underlying principle for many people who try to measure single spin orientation. Okay, so this becomes a really sort of an important technology. Now there's another way of doing these measurements. Basically, you apply a big magnetic field and you try to put your Fermi level in between the Zeeman splitting, and so you can have the so-called spin selective tunneling. And that is also a technique that a lot of people are still using. It is a very slow technique. So in the future, if you really want to develop a qubit, that probably won't be your spin measurement technique. well, this polyblockade technique might be the way to go. Okay. So armed with these two development of, being able to initialize a single electron into a quantum dot and then measure that single quantum dot, then people start to design quantum dots that can be used to host single spin qubit. Okay, so this is a typical design back in the early 2000s, where you are using gallium arsenide. It's a two-dimensional electron gas. So you do modulation doping in the barrier, right, in the aluminum gallium arsenide layer, and then you make a 2D electron gas, and then you put metal gates on top of the barrier to deplete some areas, like the holes down there, until you can get one electron in each of those puddles. Okay, and so these samples have reasonably high mobility. Turns out you actually don't need that huge mobility that quantum Hall effect, quantum Hall study is needed. Okay, because quantum Hall studies needed high mobility, and those high mobility was achieved with high doping, with a lot of carriers. So it is like you go to the shore, right? When your tide is high, the tide would basically drown out all the rocks along the shore. You don't see the rocks. Okay, the rocks are the defects or the scatterers in the system. So if you have enough electrons, it will scatter, it will screen all those scatterers. But we're trying to reach single electron quantum dot, right? So inherently, we cannot go to this large number of electrons to start with. Okay, and so it turns out, the modulation doping is actually eventually hurting qubit instead of helping the qubit. So it turns out we don't really need this high mobility. Instead, we need very clean samples with as little doping as possible. Okay, which I will mention later. And so these dot size are pretty large still, like 100 nanometer, 200 nanometer. And the gates, the width of the gates are tens of nanometer wide. Okay, so already you can do pretty good experiments. Here I just gave a couple examples. This is Coppens and et al. From Leo Cohenhoven's group in Delft. They demonstrated single spin rotations, and those were measured with spin blockade. And here is an experiment done in Harvard in Charlie Marcus' group, led by Jason Betta. These experiments were done also in gallium arsenide double dot, and the measurement also was done actually through polyblockade. Okay, and you can see you can get coherent oscillations. The quality of the signal here is, well, this one looks better and this one looks worse because this one is actually, the qubit is encoded into two spin states, and these oscillations are exchange oscillations, and exchange is charged, right? It's electrical, so the initial quality was not as good. Okay, but still, these are already by the middle of 2000, around 2005-ish, already people can do really impressive coherent control experiment on single or two electron spins in these semiconductor quantum dots. Okay, so that was sort of one big step forward, obviously. But that also was a time when different people start to argue that maybe we shouldn't be doing these experiments in gallium arsenide. Instead, we should go to silicon. So why is that? Gallium arsenide actually has a very nice, simple band structure. Its conduction band is split from the valence band by more than 1 electron volt. So it's very, very well isolated. And the conduction band bottom has a very simple structure. It sits at the gamma point in the middle of the first Brillouin zone. There's no degeneracy, no nothing. So the spin is very clean in that sense. However, gallium arsenide suffer from all the nuclear spins. Both gallium and arsenic only have nuclear spin isotopes. You only have nuclear isotopes with spin 3/2. Okay. So gallium has 2, gallium 69 and 71, I believe. Arsenic has arsenic 75. Those are the prevalent isotopes. All 3 of them has spin 3/2. Okay. So a spin qubit sitting in a gallium arsenide quantum dot basically is sitting in a sea of nuclear spins. And they couple with each other through the hyperfine coupling, the contact hyperfine coupling, right? The electron wave function is S wave in the orbital side. So you have a finite contact hyperfine coupling, which is pretty strong, turns out, okay? So basically, you know, your electron spin sits in this magnetic environment. Even at the dilution fridge temperature where these experiments are done, the nuclear spins are still in the high temperature limit. So they point in every which way, okay? So the electron sees this random nuclear environment. If that environment is completely frozen, it's still okay. You have a different environment for different quantum dots, but they give you the so-called inhomogeneous broadening. If they don't have dynamics, your qubit is still okay. But at the end of the day, you do have dynamics in the nuclear spins, right? The nuclear spins interact with each other through dipolar coupling. They interact with each other mediated by the electron spin, etc. So you have that dynamics, and that will cause the coherence for the electron spin. So in gallium arsenide, you just can't get rid of these nuclear spins. They will always be there. You can live with them, and that actually led to some very impressive experiments, very interesting experiments, showing collective dynamics of the nuclear spins. But it's more interesting physics problem from the qubit perspective. They are detrimental, right, in that sense. Okay, and so that really sort of make gallium arsenide less of a candidate in the long term. In the short term, fine. They are good samples. They have good qualities. You can grow aluminum gallium arsenide lattice matched on gallium arsenide. So all those are advantages. But in the longer term, their future is questionable. On the other hand, silicon, which is, you know, a material that is widely used in the microelectronics sector in the industry. So people have a lot of experience processing silicon and make high quality silicons. Silicon has only one isotope, silicon 29, that has a nuclear spin 1/2. The other prevalent isotopes, silicon 28 and 30, are not spinful. Their nuclear spins are 0. Okay, and that 5% of silicon 29 can also be removed through isotopic purification, right? And so that has turned out to make the system much more coherent, at least in the sense of nuclear spin environment. Okay, now silicon does have a more complex band structure in the conduction band. Its conduction band minima sits closer to the X point rather than gamma point. So there's a 6-fold degeneracy, which I will mention at the end, how that would lead to interesting physics and also headaches for manipulation. But you know, so people have gradually over the past decade moved to study spin qubits in silicon. Okay. All right. So now for spin qubits, most studies happens in silicon. So here, you know, again, I'm brought up the experiment done by the Marcus group on gallium arsenide double dot. In comparison, when you look at a similar experiment done in silicon, but this is natural silicon. So the nuclear spins, the silicon 29s are not removed. And you can see that the coherence is much improved compared to the gallium arsenide system. Okay. Now I have to say that it's probably not really fair to compare them directly. It turns out with gallium arsenide, you can also make these samples better, these signals better. But you know, when you really compare, if the two are at the same technological control level, then silicon will have better coherence compared to gallium arsenide. Okay. And these days, especially in isotopically purified samples, people have really demonstrated very coherent controls for the system. Okay, so for example, this experiment done, I think this was done in silicon phosphorus. This one was done in silicon MOS quantum dot. You can have very high fidelity single qubit oscillation, single spin oscillation, and also 2-spin controls as well. Okay. And so, you know, the experimentalists have been, you know, these are from 5 years ago, and over the past few years, there have been even more progress. Okay, so in silicon, you can also encode spins as qubit in different ways. Okay, you can have the original Bruce Kane's proposal using nuclear spins, or just using the electron spins confined there, or using quantum dots. Okay, so these are quantum dot samples. You can use silicon mass using silicon oxide systems, or silicon germanium as the barrier for silicon. And so there are, you know, all sorts of different schemes and different gate structures. Now, silicon compared to gallium arsenide, one drawback is it has a heavier effective mass for the electron. So the quantum dots have to be smaller than in gallium arsenide. And so people develop these so-called overlapping gate architectures to make smaller quantum dots as well in silicon. Okay. So, you know, we can take a step back, sort of compare where spin qubits and where superconducting qubits are. As I was saying before, you know, superconducting qubits really, there were a decade or two development before qubits were proposed, when people were trying to demonstrate microscopic quantum coherence in these small superconducting circuits. So that really laid a technological foundation for the qubit study. Okay, so starting from, you know, end of 90s, beginning of 2000, then people start to have demonstration of qubits, different type of superconducting qubits, and gradually going to showing that qubits can be coupled to resonators strongly, and design of these capacitively shunted qubits, and, you know, to now, the companies can easily make qubits that have architectures that have more than 50 qubits, right? The Bristlecone of Google has 70 something, and I believe IBM also has similar chips with similar number of qubits. Okay, so you can see that these technologies have been taking off since the middle of 2000, and now that's why the companies start smells money and they start to jump in to the fight. Okay. On the other hand, spin qubits, you know, the early proposal was really interesting. So that gets people interested in this system, but you still have to build the basic technologies. So over 5 years of time, experimentalists devised, you know, different ways to do measurement on spin, prepare the spin, etc. And so that allows really the demonstration of qubits in these semiconductor quantum dots. And then gradually that material system underlying the spin qubits also shifted from gallium arsenide to now almost everyone is working with silicon-based system. Okay, so by now, I think like one of the papers published in 2018 has demonstrated a 99.9% fidelity for single spin gate fidelity. And in recent couple years, there have been demonstration of 2-qubit gate fidelity above 98%. So it's still nowhere close to letting you do quantum computing, but you know, it's getting there, it's getting closer. Okay, but there's still, I would say, a pretty long way to go to really make this qubit system as competitive as the superconducting qubit system. Okay, now one of the advantages of spin qubit from my personal perspective is that these are small systems. Okay, the qubit size is below 100 nanometer in silicon, more like 50 to 100 nanometer. Okay, and so these are small systems that probably can be integrated more easily and to make a large chip with a lot of qubits. Although, you know, we don't know, right, in the future how the measurements are done, what circuit you need to insert to make high fidelity measurements. Those are also unknown. So we don't know how this small size of qubits can actually become a real advantage or not compared to the larger superconducting qubit. And you know, the larger qubit really are much easier to fabricate and allow more groups, academic groups at least, to study them, right? If you really have very demanding fabrication and control, then simply you just have fewer groups working on these systems. Okay. And so I think I'm running out of time already. I'm giving you a history of the system. It's already 12. Surjit.
Yeah.
Should I wrap it up?
Yeah, probably. I mean, how
Okay.
much longer do you expect?
I can skip things. It's all
yeah,
right.
maybe.
I have like I have like 29, 30 slides, but
okay.
I can certainly skip these things.
Yeah, maybe another 4 or 5 minutes.
Okay. All right. So, you know, here I'm just comparing the superconducting and spin qubits in terms of their coupling with the environment and how the measurements are done. And, you know, you can look at the historical development. The spin qubit, at the end of the day, nowadays, you can have a inhomogeneous broadened defacing time in the order of 100 microseconds. And these spin qubits are still defacing limited. Okay. On the other hand, the transmons nowadays, the coherence time can be larger than 100 microseconds, I would say, and it's mostly relaxation limited. So there's less pure defacing to worry about. So that's certainly one of the advantages of a superconducting qubit. Okay, but I would say, you know, both have been improving quite dramatically, and so one question for us is how, for us working on spin qubits, is what we can learn from, you know, the development of superconducting qubits, particularly in terms of how we can shield our system from charge noise. You know, even we have spin qubits which are magnetic, it turns out charge noise is really important because, you know, coupling of spin qubits is electrical, right? Exchange interaction is Coulomb interaction plus Pauli principle. So, you know, charge noise can still affect your system pretty strongly if you don't pay attention. Okay, so there are multiple things we can certainly learn from the superconducting qubit studies. Okay, so let me just mention one thing about what I have studied. You know, silicon, as I mentioned before, have 6 conduction band minima, and this give you extra orbital dynamics. For a spin qubit to work properly, you need to freeze out the orbital dynamics. Otherwise, you know, through spin orbit coupling, you would mix the 2 degrees of freedom, and then that will hurt your spin qubit. What happened in silicon is when you actually do put the quantum dot near interface, just because of the anisotropic effective mass in silicon conduction band, you will actually select 2 of the valleys to be the ground valley. Okay, so the other 4 will actually rise up in energy near interface, near the interface confinement, so that you don't need to worry about them much. And then the interface scattering can couple these 2 leftover valleys and give you a so-called valley splitting, which typically is in the order of 10 to 100 micro electron volts these days. It can go higher, a few hundred micro electron volts in silicon MOS system. But you know, this is a quantity that we have been concerned with. In a single quantum dot, it's mostly concerned. We are mostly concerned with how big this splitting is. But when you go to multiple quantum dots, then the sign of this coupling, or to be more precise, the fact that this coupling is actually complex, so the phase of this coupling becomes more important. Okay. So for example, if you have a double quantum dot, it turns out the tunnel coupling relates not only to how high the barrier between the dots are, but also relates to what are the phase difference for the valley coupling in these 2 dots. Okay. Now, in the early days, we assume that these valley couplings the phase difference are minimal, so we don't need to worry about them. Okay, but it turns out in some recent studies, including a study done in my group here, this is done by my student Bilal Tariq, where he studied how just a single step on the interface could actually cause the valley splittings to be strongly suppressed if the step happens in some certain positions. And the phase difference, the phase in the valley coupling phase can also change dramatically depending on where that step is in the quantum dot. Okay, and so that led to interesting physics where if you put a 2 quantum dot in there, put 2 electrons in there, the exchange splitting can actually go from a finite value down to almost zero because of the fact that the value phase are different across these double dots. So that's something that we would actually have to fight against if we want to make a scalable system with many quantum dots for the spin qubits. Okay, so let me just conclude here. We have gone pretty far in the study of spin qubits in silicon, but certainly there are still a long way to go before we can say that this is a system that is competitive with the superconducting qubit. Okay, so in terms of a universal quantum computer, irrespective of what qubits you have, I would say we're now in the so-called NISQ era, so the noisy intermediate scale quantum technology. I think John Preskill coined this name. And basically, you can have 100 qubit or even a few hundred, maybe even 1,000, where each qubit has very good coherence, but these are systems that are not fault tolerant. So they will decohere. Okay, so if you have a larger system, they will decohere pretty fast. Okay, and there's no error correction yet that has been implemented to really maintain the coherence of the system. There are experimental demonstrations, but those only shows that you can reduce the decoherence, but not remove it. Okay, and superconducting qubit certainly is way ahead of everyone else, but I don't think the race is over yet, right? A spin qubit or maybe some other type of qubit, for example, topological qubit, which has been really hot for the past 10 years. Who knows? They may turn out to be the ultimate qubit. Okay, so I would say spin qubits probably are at this stage where we have paper planes. We can show they can fly, right? 1 qubit, 2 qubits. While the superconducting qubit maybe is at this stage with the Wright brothers plane, where you can carry a person and fly for 100 meters, 200 meters. We're still pretty far away from a real universal quantum computer, but it seems like we may be able to get there. So let me just stop there. Thank you.
Thank you, Xuedong. That was a wonderful talk. And now we are open for questions. So let's fire away.
Yeah, I guess I sort of gave more of a historical perspective than what we have been doing, really.
But I think this is wonderful because that's, this historical perspective is not easy to come by. You also give a lot of physics along the way.
Yeah, and, that's for sure.
Yeah, and you and I have discussed a little bit, but we haven't really, I certainly don't know much about it. And the whole issue of decoherence is exciting to me because relaxation problems I've worked on. But, controlling decoherence is a completely different problem.
Yeah, so people did come up with multiple schemes to fight against decoherence, right? From first, just engineering the environment, make the environment better, and try to remove those effects. For example, moving from, in the early days, all the quantum dots are made with modulation doped samples. So you leave all these ionized nucleus in the barrier material, they become Coulomb scatterers, right? So they give you this order at least, and some of them could give you noise. And to nowadays, all the samples are made with accumulation mode samples. So you don't dope the system at all. You use a gate to drag electrons from the reservoir into quantum dots.
Yeah.
Okay? So that way you remove a huge chunk of possible charge fluctuators.
One of the questions I had, and it's a very theoretical point, is we know that when you have Heisenberg type couplings, then all kinds of complexities arise. Whereas when you have Ising type couplings, then the problems are somewhat more manageable. So I'm just curious as to whether much work has gone in the direction of developing systems that are more Ising-like vis-a-vis more Heisenberg-like.
Right. So if you make two qubits actually off resonance, you can make that interaction more Ising-like than Heisenberg-like. In fact, in the liquid state NMR samples, because all the spins are off resonance, their effective magnetic dipole coupling becomes Ising type. Also, when you have qubits coupled with resonators, right? You can couple resonators, different qubits to a resonator. The effective coupling between the qubits turns out to be Ising type too. Okay, well, could be Ising type, could be XY type, etc. And so certainly there are ways you can make them more Ising-like. But for the two qubit gates, it turns out either one is fine. Anyway, you just by the interaction itself, you can't really do a two qubit gate. You have to associate it with also single spin or single qubit control. Together, you can construct a two qubit gate, whether using Ising or Heisenberg, without too much extra complexity.
I see. But if you have a many spin system, wouldn't things change?
So the so-called quantum circuit model, which is at any particular time, you're only coupling a pair of them, well, or many pairs of them, you could certainly do that. But, you know, so you're not, you could in the certainly when you do quantum simulations, you would probably turn on a lot of interaction. But for quantum computation, probably not. So then again, you're just depending on, you know, back in the late 90s, theories showed that as long as you can do single qubit and two qubit gates properly, then you have universal quantum computer.
Okay. Questions? I'm not hearing questions today. But you obviously gave a wonderful talk. People understood things. That's not
enough physics.
A lot of physics.
Yeah.
There's a lot of physics, but I think people are being a bit coy today.
Yeah. So you know, spin or qubit physics is somewhat, I should say, it's more like quantum optics, right? These are weakly interacting systems that you can study with perturbation theory most of the time. There are certainly interesting problems like nuclear spin problems where they are all coupled, so you have a strongly coupled system. But in many other, especially for qubit themselves, you want them to be isolated from the environment. So then whatever the coherence effect should be a perturbation. If it is not, it's not a good qubit. So then the physics is bound to be different from all the, you know, more fashionable, strongly correlated physics that you study.
Yeah. So at a more sort of practical scale, I guess, I'm just wondering, I mean, I'm going to stop boring you and stop the session now, but I'm just wondering that in the next 20 years or so, where do you think we'll be in terms of fairly sophisticated, clean quantum computers?
20 years is a long time. If we go 5 years, I would say you probably with the superconducting qubit system, they probably can reach 1,000 qubit. They could probably do some simulations, quantum simulations with them. I don't know whether, you know, a decade ago, I think, at least 5 years ago, there was a program, so-called Logic Q, where people were asked to demonstrate logical qubit. So on the way towards the so-called fault-tolerant qubit, where after quantum error correction, you can keep all the coherence of a qubit, right? I don't know where it has gone, like how far that program has gone. So I don't see a logical qubit being demonstrated yet, but maybe within 5 years, that can be demonstrated, or maybe 10 years. So for a small scale system, you probably can demonstrate that you can reach fault tolerance limit. that would be huge in the sense that now you can make a qubit and let it live forever, right? How you can scale that up, that's something I don't know, because a logical qubit typically would have many, many physical qubits in it. Okay, especially if you concatenate. So you can have a couple thousand physical qubits making one logical qubit. But to demonstrate really clearly quantum error correction and also fault tolerance, those would be probably the most important task over the next 10 years. So in 20 years, if this is done, if fault tolerance can be done, then in 20 years, we would have a quantum computer, a real one. But I don't know whether that can be done or not. Or,
well, look at it this way. In 10 years, you can own a quantum calculator.
But those are useless, right? For all the calculating, like as I mentioned at the beginning, for most our daily tasks, or for almost all our daily tasks, we don't need a quantum computer.
No, you don't, but you can.
So unless you want to break someone else's code and steal their credit card number, you don't need a quantum computer.
Not really.
Right. So the, you know, you can just live with the current
real quantum systems, which are hard to simulate. Then it can be.
Yeah, I think that's sort of the first real useful demonstration or use for it is to simulate, for example, whether for physicists to simulate lattices or for chemists to simulate reactions and catalysis, whatever. Those probably would be the first useful applications of a quantum system.
Yeah, I can imagine there is strong defense interest.
Let's say we can do Howard model calculation with this. Does it really helpful? Is it really helpful?
I don't know, like in what sense would it be helpful or not?
I mean, you can solve large lattice, and I mean, people are trying to do this.
Yeah. So that even now people have started trying. But you know, with cold atom physics.
I don't know whether you realize Hubbard model with optical lattice or quantum computer, you solved it. And yeah, then you can tell, okay, the model has certain this and that properties.
Yeah.
Right.
Does it really help us understanding real natural system?
I don't think so. Those are still model simulation problem, right?
Yeah, it's toy model still.
Yeah, exactly.
Actually, John brings up a good point, because one of the things that, I mean, in condensed matter, these toy models have been quite successful. I wouldn't use the word enormously successful, but quite successful in improving our understanding of how quantum many-body systems tend to work. But real systems that we encounter are not toy models, right? But if one could actually simulate the toy models really well, then
it is like I mean, still with classical computers, we do quantum Monte Carlo, for instance.
Simulations,
has given us a lot of information and taught us a lot. But I mean, it is actually it's a philosophical question more.
Yeah, I mean, if you do a
and even if we know how things are going to behave, and can we call that, say, do we understand it?
Yeah.
Yeah.
But lots of simulations will be
fair,
needed.
certainly fair question there.
Yeah.
So personally, I think, you know, in physics, I don't know how helpful it would turn out to be. In chemistry, maybe, you know, people were talking about simulating different catalysis process or reactions.
Different mindset.
Yeah. So I guess we'll find out. We'll get there, and then I'm sure someone will try to take advantage of whatever is available, right?
Oh,
you know, just generating random numbers obviously is not useful at all.
I think it's a more philosophical question, and that limited to our lifetime, I would say. In my lifetime, do I understand anything? Do we understand anything? And eventually it may, once things accumulate, then there may be some phase transition of understanding. But,
yeah, maybe we'll just teach it to AI, make a quantum AI that will help us discover new physics instead of what we can.
Yes. Well, thank you so much, Xuedong.
You're
Let's
welcome.
close it, and this has been a lot of fun. By the way, next week, next Saturday, we have Vittorio Loreto. Vittorio, for those of you who don't know him, he's famous for his TED Talks and everything, but he has been one of those physicists who has spent a great deal of time working on modeling social systems. He has a very well-known reviews of modern physics. He's now director of a complexity center. He's from Roma Sapienza. I haven't met him since he was a graduate student, but it will be hopefully a fun presentation next Saturday. So hopefully you guys will join us. So thanks again, Xuedong.
You're welcome.
Loved it very much.
No problem.
And I'm sure people did as well. All right.
Thank you, everyone.
Bye-bye.
Bye.